Hey everyone, I'm John Abercrombie, and Damian Isla is right over there. So I'm going to start with the first part of the talk. But like Dave just said, procedurally generated worlds and player building are huge parts of games today. And both Damian and I come from a background with more like very much designer-driven, handcrafted content, and we both moved into this new and interesting phase of games that have randomly generated worlds in it. And so our goal, I think, for both of us has been try to take some of that richness that comes from that handcrafted, content creator placed pieces of the game and bring that into a space that you really don't know much about when you start the game. So I'm working on a game called Fortnite. It's in alpha testing currently. We're moving towards bringing it out very soon. But basically, the game is about player building. Players build forts to save the world, and you have to defend against the invaders who are coming for your fort, basically, and for the thing inside the fort that you're protecting. And then you have a bunch of people that you're rescuing as well in the game. So while I could talk about it more, I'm just going to show you a little video, and you can kind of get an idea of what it is. But one more note, I just want to make sure you all know, it's a multiplayer building action survival game with RPG elements. So there's a lot going on here, and you'll see that in this video. Of course, the video is not safe for the audio right now, so let's move past that. So I came to Epic Games from Irrational, where I worked on BioShock and Infinite with Elizabeth. But I came to Epic to solve, face new challenges and work on difficult problems with a bunch of talented developers. And there certainly have been many to overcome, especially when it comes to the procedurally generated aspect and the player-generated aspects of Fortnite. So I'm going to approach the talk from the perspective of some of the problems that we've had in building this game and then how we solve them. So, these are examples of techniques that we've used for the procedurally generated and player-built structures in the game Fortnite, and they're useful techniques for the game we're making. They may not necessarily be useful to you, and I've tried to pick the techniques that will be most applicable for the general case, and I include both development techniques as well as runtime techniques. So while all of these techniques may not be useful to you right now, I'm hoping that you'll have at least something to take away from this talk. So worlds in Fortnite are procedurally generated and stitched together at load time using a random seed. So they're comprised of level designer, worlds are comprised of level designer levels that they've been handcrafted a little bit and then streamed together, stitched together, and then they have a lot of potential locations for gameplay. We run the game on a dedicated server. Like I said, it's a multiplayer game, and we don't have access to the renderer. So the AI logic exists only on the server. So debugging problems becomes pretty difficult beyond the text output that you can get from a server. So we wrote a system to allow the recreation of the procedurally generated levels in the editor. So that allows running worlds that are normally run in the client-server situation to be just run inside of the editor. And it's incredibly more powerful to have access to have it in the editor because you can run it repeatedly over and over again really quickly. And having access to a debugger versus a log file is, well, I don't have to tell you how much better that is. It's really a much better situation. In Fortnite, once we've loaded our randomly generated world, we need to allow the AIs to be able to navigate in it. Then the players load into, and then they start building. So how do we deal with that? Well, like most games these days, we use the standard navigation mesh. In fact, we're using Recast. So we use what we call nav links, which are also called off-mesh connections in Recast, and it allows AI to drop off the ledges or move through geometry or move between edges of the nav mesh and generally improve connectivity. And the nav mesh responds quickly to player-built structures. So we build the nav mesh in a tile form, and hopefully this video works maybe a little bit better, but you'll sort of get the idea as I play it. This is, again, standard warning for today that this is debug level. The game may not look like this. It probably won't. This is a debug level. And so what you're seeing here is the sea of blue is just the navigation mesh. And then the red is where we're one of the tiles that we're rebuilding. And these green areas that you can see, and we have a few other different colors in here, you can see where we've added cost to the navigation mesh so that AIs will try to avoid those when they're doing a path find. But there are lots of, we want to have lots of AIs in Fortnite, and, and the AIs are traveling long distances. So the nav mesh is great, but all those triangle traversals can get expensive. And we could use maybe cached paths or something like that, but that only works, if the AIs are all traveling along the same path and the paths don't change. So that doesn't really help us very much because the paths are always changing in Fortnite as the players are building. So what we did was we had to have an alternative connectivity graph. So we call it the navigation graph, and it's based on the bedrock of the level, of the navigation space of the level. And we do have some allowance for dynamic nodes as well, but most of it's based on the bedrock. And the graph nodes, they describe the space and the connectivity to the other nodes. So here you can sort of get an idea for what the nav graph looks like. Since we're built on a tiled world, the graph nodes are built to the tile size. So all these white boxes are nodes in the navigation graph, and then you can see maybe a few blue ones that are actually dynamic. But there are still lots of nodes in the navigation graph. Certainly less than the number of triangles that we're dealing with in the nav mesh, but the navigation graph still isn't fast enough to allow us to have a large number of AIs traveling long distances. So while it describes the connectivity for us in a much better way, we can do better. So since we know where the AIs spawn and then where they're going to generally, we can use the navigation graph to generate flow fields. And then once we have those flow fields, we can basically create reusable paths along the navigation graph that the AIs can follow over long distances. So for performance reasons, we can generate the navigation graph in the editor. We don't need to actually do it at runtime because it's not based on any of the player building. But the flow fields are generated as an initialization step to our encounters, and then our paths are generated from that flow field. So basically we use a Dijkstra flood fill of the navigation graph and to determine connectivity. And then, from the flow fields, we extract the paths based on where we will spawn the AIs. And so here, if we look at this again, you can sort of see those red lines. And that's after we've done the flood fill. So from there, we will pick our spawn points, which will end up being, in our view frustum, those clouds. And now we've taken and created the paths here. And we have the paths from where the AIs are spawning to their goal where that beam of light is hitting the ground right there. And note that is the optimized path. There's actually no direct way up, so they have to actually cut around and come back. They can't actually climb up terrain, well, yet. In Fortnite, players, they also can build structures almost anywhere. So we're dealing with not only the randomly generated worlds, but we're dealing with players who can build almost anywhere. And they can, they build their player-built forts. They can build walls, floors, ceilings, and more to stop the AI from sabotaging, stop the AI from navigating to their goal. So the way we used to have the AI attack structures when I first started was to just have them sort of bump up against a piece of geometry and start attacking once they got there. And it was absolute chaos. It really looked bad. It didn't have good results, and we needed to solve that problem. So the solution was, for us, was to add what we call hotspots. It's basically an offset position and orientation from a building structure. We make mixed use of both baked in editor sets of hotspots as well as generated on the fly in the game to allow the AI to attack structures. So they can be socketed about geometry. For Fortnite, we choose hotspots based on the direction we're approaching from. So we actually have hotspot sets from each direction you can approach a building structure. So if you took a wall, right, you can approach a wall from 6 different directions, and for each of those directions, you would have a different set potentially. So we have that pre-baked data, but once you put all those structures together, we have to filter that with runtime tests so that you can make sure that if I want to go to this hotspot, can I actually path to it? So some hotspots are ignored because we can't path to them, or if they're blocked by geometry or another building structure. Hotspots are also a good way to make the animations line up with geometry. While it's not going to be exact, we're not really trying to be perfect about that. We want it to look good. It works very, very well for that. And sorry, one second. So, although we use the hotspots for having the AI attacking building structures, the hotspot technology isn't limited to that. You could use it for having AIs going up to interacting machines or something like that. It's something we're looking into for the future. So here's an example of hotspots in action. This is an automated test level, this is our automated test level for hotspots. And you can see right there, there's a big tree, and the AIs in this test have been told to destroy the tree. Now, about the tree, there are a bunch of hotspots, and there are actually a bunch of AIs in there right now. That tree is very large. And the hotspots about the tree that are further away are actually for ranged AIs to attack the tree. So ranged AIs that have the capability of destroying building structures can do so. And we also have some hotspot slots as well for the larger AIs that we have. So like I said before, the players can build structures pretty much everywhere, and we don't know where anything is going to be in the editor, except for the indestructible floor surfaces. So we have no chance of pre-calculating 100% effective data ahead of time. That's very different from the projects I've worked on before, where we've been able to do a lot of the baked calculations ahead of time in the editor. And the complexity in the player building situations can become too great a problem. So you can see here, you have a bunch of AIs with the hotspots. The AIs are mostly underneath this structure, and they're trying to path into that pyramid up above. And it's a complicated situation where the AIs are trying to navigate into the pyramid, and they're destroying the structure below, and it can get really complicated. And once things get more complicated when dedicated players start building, they have a lot more time than I do, I guess, to create crazy structures. So you can start to see that here, and then this is just massive structure there. So things can get really complicated. So as a result in the AI, I think it's better to be good and work all the time than perfect and fail when it comes to the character's performance. Robust solutions are important. Players are novel, and we want to allow them to be creative. So one of the things we do is a daily use of automated tests. As I mentioned, that automated test level we had before. When we find issues with the AIs attacking things, for example, we will create a new test based on that. Pretty much every AI system in Fortnite has at least one fallback behavior to deal with the complexity, so navigation, behavior, goal selection. And during development, it's also important for us to know that the AI are actually failing, so we actually have an additional behavior to show that, which is for development purposes only, but at least we can see when the AI is failing and moving to a fallback. And eventually, if the AI fails repeatedly, we know there's a really big problem. So the last problem I wanted to talk about was that there's very little domain knowledge to make decisions. Like I just said, previous games like SWAT 4 and Bioshock Infinite, they used a lot of designer-placed points to describe domain knowledge to the AI. And in a procedurally generated action game, this really isn't as possible. Positions and orientations, they'll be different from run to run. And then you add in player-built structures, and I don't know, you just got to deal with it. So we make heavy use of real-time spatial feature evaluation in Fortnite. So it allows AI to understand the current world configuration, including player-built structures. And I think the line from Jamie Griesemer and Chris Butcher's talk about Halo 1 still rings true, which is that reasoning on a continuous space requires discrete sampling points to make decisions about that point's effectiveness. So just to show you how we do it in a basic way, we generate points in the world. We'll project those points to a surface. You can do it to geometry, the nav mesh, or you can do it to both. And then you can test those points, to filter and to score them. Tests can use external values to compare distances, dot product, whatever you want. And we're not really just limited to points. Results can come in many forms: single best result, multiple sorted results, etc. And so we use real-time evaluation for all sorts of things. We do it for encounter layout, so that we can pick the best direction for the AIs to approach from. So we can pick a spawn point, so that we can put a patrol about players, so that we can position, which is a typical use of spatial reasoning in games, even static worlds as well. We also do it for goal selection, so what's the most important thing for the AI to be doing right now? And then just doing some evaluation for the AI director. So for us, spatial reasoning also needs to be performant. We want to run lots of servers for Fortnite, minimal CPU usage times. So we have a spatial reasoning budget, and we are constantly doing performance analysis to make sure that everything's going at using the correct amount of resources. And then, in general, the methodology I've given to the team is that we keep the spatial reasoning tests simple but effective, so we're not, again, using too much performance. So here's just a little bit more picture of Fortnite, just sort of having it all come together. And that's it. Thank you.
Okay, am I live? Okay, so hi, my name is Damian, and I also have a AAA background. Worked on a number of games in the past where you shoot people in the face from a first-person perspective. In fact, we worked together on BioShock Infinite for almost a year, a couple years ago. But in recent times, I've actually moved into the indie space, so I'm going to be talking to you about a game called The Flame in the Flood, which came out about 3 weeks ago. So The Flame in the Flood is a survival roguelike game in a procedural world. In this case, it takes the form of a soulful river journey down sort of this post-societal Mississippi River. Kind of a Don't Starve meets Journey, or maybe Huck Finn meets The Road, or something like that. Tubin meets Oregon Trail is the one that my coworkers really like. I never played Tubin, so I don't know that one. But so you float down this procedural river, and the idea is that you stop at various sort of recognizable locations, and each time you get off your raft, you have a little micro world that is populated with things like plants to loot, locations to explore, AI to combat or deal with in one way or another. So just to give you an idea, so I'm going to be talking about the on-foot sections, what we call Explore Islands. I'm going to be talking about that section. If you want to hear about the river generation part of it, I'm giving a talk on Thursday in the main conference about that, so please come to that if you're interested. But I'll just give you an idea of what those on-foot AI look like, the Explore Island AI. We put together a helpful survival guide for everyone. Does it help if I start again? This is playing at about half speed for some reason. Can we just mute the audio, because the audio doesn't match at all what's going on? What this should be showing is just basically sort of the kinds of interactions that you have with the AI and the AI have with each other. Okay, well, forget this. It's getting slower as we go. So part of the idea was actually inspired by some of the early pitches I heard for BioShock, where the talk was of taking these different kinds of characters. They have their own sort of internal behaviors, their own way of seeing the world, their own way of interacting with their environments, and you just sort of sprinkle them into the environment together, and they interact the way they will interact, and the gameplay comes out of the player coming to learn what the rules of behavior were and learning to exploit one AI against the other. So we were interested in that. We were going to do something similar with wolves and bears and snakes and that kind of thing. But of course, okay, if all of the intelligence is wrapped up in the AI itself, then where does sort of the encounter logic live? Because that's typically what a designer would be authoring, a level designer would be authoring within an authored environment. So for us, the encounter sort of consists of things like resource spawning, certainly AI spawn locations, AI territories and how they relate to their territories, and the spatial behavior that the AIs exhibit. So here's what an Explore Island consists of. It's a very small, relatively small, closed arena. It's got a single entrance, and it's got a series of what we call sockets, where basically pieces of geometry, particularly functional geometry, so a church or a bus to sleep in or a water fountain or something like that can be swapped in and out of. And then, other randomized geometry. Sometimes levels have, these environments have like standing water, like puddles, and heat sources like campfires and so on. So here's an example of sort of one of the larger Explore Islands. Towards the bottom left is where the player is entering the space. And you can just kind of see that it doesn't change a lot, but it changes enough, the topology of the space changes, and it changes enough that the thought of scripting or having designers put in hand-authored metadata of any kind, it kind of seems like it's not the right thing to do. So we're going to do some amount of spatial analysis to figure out how to place an encounter within that space. Now, our design goal, I actually think back from, I used to work on the Halo games, and one of the design principles for encounters there was always that the harder you push your way into an encounter, the harder the encounter should push back. And that's sort of something that I think I've always taken with me. And in the case of the Flame and the Flood, the way that I interpreted that was that the farther into the Explore Island you go, the more dangerous it is, but also the greater the reward. So, like I said, we don't know a lot. Not a lot is fixed about these spaces, but we do know some stuff. We do know, for example, because of the runtime nav mesh generation from Recast, we know what space is traversable. We know where the single exit is, because that's one of the few places that we can have a designer mark. We know where the primary location is, and some of those other features that I mentioned. So our approach is going to be to take that navigable space and break it up into a regular square grid, probably the simplest spatial representation you could possibly hope for. And using that grid along with the Dijkstra's algorithm, which John also uses, we're going to create a bunch of spatial features. And those spatial features usually take the form of distance maps. So I'm going to create one map over that space which says distance to edge. So for every cell in that grid, how far am I from the edge of the grid, of the navigable space? For every cell, how far am I from the exit? Distance to water, distance to territory, etc. And so I think if we had been sort of smarter, we would have made the system, the very same system that does spatial analysis for runtime positioning for AI, be the exact same system that did spatial analysis for spawn point generation and that kind of thing. We didn't do that. We should have, but we didn't do that. But many of the same kinds of is that 5 minutes? Many of the same kinds of decisions are made in that way. So here's the example of one sort of typical level. We'd take this open space here. Here's the discretized grid of it. Those blue squares are the ones that are in water. And then, here are the different features that we can generate. There's the distance to edge. There's the distance to exit. There's the distance to the water's edge. So both distance in water from the edge of the water and distance out of the water to the edge. And there's an example of a generated AI territory, along with the distance map for that. So right off the bat, one of the things that I sort of came to realize was that distance features are always way more useful than binary features. Even though something like territory feels like a binary feature, like is this cell in the territory for this AI or is it not, it's so much more useful to, rather than just saying yes or no, to actually give a distance to the territory. Now, one good reason for that, for example, is for using hysteresis for territory. So, for example, if I have a behavior which says, if the player stands on my territory, then attack, and then stop when they leave my territory, it's always better to use some level of hysteresis to say, not just is the player not in my territory anymore, but is the player outside of, say, 5 meters from my territory, so that the player can't dance back and forth over the line and turn that behavior on and off. So here's an example of how we do loot spawning. Plants, it's a sort of higher level authority that decides which plants should appear on a given island. And designers are able to sort of specify min, max, and average intervals for appearances of certain things. So saplings appear on average every 3 islands, but never more than 6 islands, that kind of thing. But more interesting is, like, how do we decide spatially where to put those plants? Well, certainly we can sort of specify ranges for the different spatial features. So certain plants like to spawn on the border of the navigable space. Others like to spawn in open space. But the thing that I think that is sort of more interesting that we did was to sort of connect the rarity of the plant to the distance from the exit, so that as the player sort of enters the space, the common plants are right around, clustered around the entrance. But if they push their way all the way through the space and get to the sort of the most dangerous extents of the space, that's where you're going to get the rare and powerful plants. So if the scheduler had decided, well, we're going to spawn saplings, dandelion, yucca, and devil's trumpet on this particular island, it would literally divide up the space in these 4 tranches and randomly spawn within that area. And of course, that supports the sort of design goal of the farther into the space you get, the greater the danger, the greater the reward. So are we out of time? Just roll it. All right. Thanks, Dave. So for AI spawning, we do something similar. One simplification that we do is that we don't evaluate spawning criteria on the individual cell level. Instead, we generate a series of points basically from a jittered hex grid, and we put those points down, and we consider only those locations. We can, of course, get the feature maps, all the feature values for that point either way. So it's just a way to sort of reduce the number of points that we're considering. And then once we have those points, each different kind of AI is, of course, going to have its own spawning criteria and its own sort of territorial behavior. Rabbits will spawn in clusters along with little burrows, and every time they get scared, they run back to their burrow. Wolves will spawn around the primary location, sort of guarding the primary location, and then once alerted, will just harass you until you're either dead or you leave the island. Bears are one of my favorites. They spawn in a bear den, and they're not easily aggroed, but once they are aggroed, they literally have to kill something before they will go back to their spot. So usually you can drag a bear into a pack of wolves and then sit back and watch the show. And boars spatially are maybe the most interesting example, actually, because what we do for them is to sort of generate an explicit territory for them. So here's an example of that. We know, given the space and given the distance map, what the farthest point from the exit is. And so what we do is we consider a range from 60% to 80% of that farthest distance. And we pick a point within it and just draw a line there. And we say, okay, anything beyond that is boar land. And offset from that, we pick a spawn point a little bit so that the boar is always sort of standing around towards the front of its territory. And as you come in, it's always sort of right there to challenge you. And again, sort of defining that territory as a distance map also lets you do things like create a behavior such that the boar always tries to position itself, no matter where you are, no matter how far outside of its own territory it has followed you, to always position itself between you and its territory, so always pushing you back away from its own territory. So that's the basic idea. You know, those specific examples of like how a rabbit spawns versus a wolf, of course, are irrelevant probably to you. What's more interesting is that all of those criteria are defined in terms of those spatial features. That's point number one here. And again, distance features. Whenever I have found myself saying, oh, I can get away with a binary feature, I found out 3 days later that, in fact, distance feature is much more interesting, much more rich. So again, once you have those features, you end up using them both for spawning criteria, territory criteria, and also runtime positioning. Number 3, Dijkstra is always your friend. You know, when all you have is a hammer, everything looks like a nail, and Dijkstra has been my hammer for the past couple of years. And just in general, like, you know, there are not a lot of tight constraints beyond what I just described on how things are placed out in one of these spaces. But one of the things we do, of course, is we sort of exploit the player's tendency to interpret meaning behind placements. And as long as the space is small enough and the simulation dense enough, it ends up feeling sort of fun and structured, which is what we've been going for. So to bring it back to the grand question of this whole talk, how do we generate encounters? How do we go about generating encounters without designing the encounters? Well, the fact is we are still designing the encounters. We're simply designing them in terms of abstract spatial features rather than concrete spatial features that are placed by a designer. So we didn't go too much over, hopefully, but that's where we are. Thank you very much.